So, and he will talk about, so please let me remind the title. Sorry, it's...
It would be a strong measurement for quantum trajectories, I think.
Okay, great. So please go ahead.
Okay, thank you very much for the invitation. So I just arrived to HSC since this year. Even if I was visiting HSC before, but it is the first time that I am really here. I have some contract for at least 1 year. I can share my screen, yes?
Yes.
So now I have to do it. Yeah. So I think that now you see it in a full screen, yes?
Yes.
Yes, okay. So the subject I would like to discuss today is quantum trajectories in strong measurements. So it is related to quantum mechanics. So the origin of the work is motivated by quantum mechanics, but at the end it is something more general, which is related to stochastic differential equations. So this is a joint work that, okay, several works that I did with people from France, exactly from Toulouse, from Nice, and also from UK. So these are the collaborators which appears here in the pictures. So first I would like to explain what is basically a quantum trajectory. And even for people who don't have some background in quantum mechanics, and even if you don't understand the first slide, it's not very important. At the end, you will see just some stochastic differential equation. So the basic, okay, some way to introduce quantum trajectories is the following. You have some quantum system, which is here, and maybe you can interact with some thermal bath, trying to fix the temperature of the system. And the system is interacting with some probes, so some basic unique quantum system, which are coming one after one to interact with the quantum system for a very short time. Some very short time, but with a very strong interaction. And then they go away, and then there is some observer which is looking at the state of this probe. So is recording the state of this probe. And because of the entanglement properties, the fact that you measure the probe gives some evolution of the system, the quantum system itself, even if you don't measure directly the system. You measure just the probes, but it modifies the evolution of the quantum system. So it is just some picture here. You see, sometimes it is a very simple probe where you have only the spin, which is going to be -1 or +1, and you measure -1, +1, -1, +1. And this gives some information about the evolution of the system. And okay, that is a basic system in which is discrete time in some sense, because each unit time you send the probe to interact with the system, then some other one and some other one. And then if you perform some scaling limit in which you send a lot of probes and the interaction time is very small, but the interaction time is very small between the probe and the system, but the interaction is sufficiently strong, then you can see some evolution of the quantum system in continuous time. So it is not something that I want to explain here, and it gives the name of what we call the quantum trajectory of the system. And the intensity of the measurement, which is very strong, okay, it depends in which unit, but basically is measured by some parameter which is called gamma, that we will see along the slides. So if you forget this picture at the end, what you get for a quantum trajectory is wait, I cannot look at yes. So what is the goal? The goal is to understand the behavior of the quantum trajectories that I will describe a bit later in the strong measurement regime when gamma is going to infinity. So you are measuring the system very strongly. Okay, you're measuring it a lot. So for me, at least, the motivation came from several papers which were published by some physicists, Michel Bauer, Denis Bernard, and Antoine Tilloy, essentially from Paris. And we want to understand what is this behavior of the quantum trajectories. And there are some special phenomena which appear, which are of interest also for people working in stochastic differential equation. And you will see at the end that there is also some application for filtering problems.
Okay, so sorry for interruption, just a quick question. Okay, from the first principle of physics, the quantum particle do not want to be measured and controlled too much. That's some very general physical principle. So it's easy to imagine that if you try to control it all the time very strongly, as you said, that it will jump between positions where it can be controlled. That's what you want to display, or some other idea.
So you are thinking about Zeno.
There are positions in the phase space where you cannot measure it, so the particle will be frozen when you put the jump to some other position where it cannot be controlled, or something like that. Okay, or not? Or
yes, exactly. It is a Zeno effect. You are mentioning the Zeno effect, but we are doing it in the way. Okay, we are measuring it very strongly, but for a very small time, so we avoid the Zeno effect. So the system is not frozen. We have to do it very quickly. It is a special ratio of the interaction on the time in order to avoid the Zeno effect. Because of course, if you let the probe interact with the system for a long time, it will thermalize at the end. But here we are doing it in a very special way in order to avoid this effect. And it is the reason for which we have some evolution of the system which is not frozen. I don't know if my answer is clear.
May I also ask, I'm Shiryaev-Vonham, also from High School of Economics. Probably the good thing here is to assume that we measure some small part of the whole population of qubits, or we have only one qubit here.
No, you can have only one qubit, for example. It is the
only one qubit.
Example here is one qubit. The important fact is the ratio between the time of interaction and the intensity of measurement. It's true that if you don't regulate this ratio correctly, you could have something which is frozen. Zeno effect. It is a Zeno effect.
Okay.
But here we are doing it in special way in order to avoid this Zeno effect and to avoid to have some just free evolution.
Okay.
So it is a very special
some
regime.
kind of new physics. I learned that the measurement is instantaneous, but okay, let it be some new physics where we can avoid Zeno effect.
Yes, the principle is to avoid Zeno effect.
Okay, so now we assume that measurement is not instantaneous. It takes some time, and if the time is rather small, we can avoid the effect. Okay.
Yes, exactly.
This is
exactly.
some kind of axiom.
Yes, yes. But mathematically,
Thank you
you
very
can
much.
precise very precisely what it means.
Okay, thank you.
So I give some example of exactly what you said before. It is a qubit. So if the rest of the talk, in fact, if I want to describe my quantum system, I describe it by its density matrix. So density matrix is a matrix which is Hermitian, which is positive with trace 1. And it describes the state, okay, in my spirit at least, in my mind, it's described the state of the quantum system. So for example, if you have a qubit, so a system of quantum system with two states, so it is described by a matrix of this form where you have x here, 1 minus x, because the trace has to be 1, and it is emission, so you have y and y star. Okay, so that it is emission positive and positive emission and of trace 1. So it is the typical state of the system. So the off-diagonal terms are not so important because you can show that in the strong measurement limit, when gamma goes to infinity, they will go to 0. So they will not be very important. What is important is the diagonal terms. And these diagonal terms, of course, they are of the form x and 1 minus x, because it is of trace 1. And so we are interested in the form, what is the limit of his x as gamma goes to infinity. So here it is a qubit, which is in contact with a thermal bath subject to the measurement of the spin of his qubit.
Excuse me, do I understand correctly that you have the system with two states, xt for you is the probability that you measure one state on another state, so it's go between 0 and 1 for you, xt, right? And okay, this is density matrix. And the question is, you can either write stochastic Schrödinger equation, study it, or write a dynamic for density matrix. What, is it correct what I'm saying or not? The sense of st is a probability that you measure the state 0 or 1, yes? Or, okay, suppose state
yes,
0.
You measure the spin. You measure the spin.
Okay, correct. Okay, so x between 0 and 1 for you.
No, it is between 0 and 1.
Okay, thank you.
And so in this system, you have just a qubit, which is in contact with some thermal bath, which try to fix the temperature of the qubit. But you are also measuring by some probes, like I show in the first picture. You are measuring the spin, but indirectly by measuring the probes. And so if you start from the initial model and you derive this scaling limit, you obtain this stochastic differential equation, which is quite simple, and it will be one of the main equations that we will consider in the cycle. So as you can see, the effect of the thermal bath, so which is represented by this drift term, is that it tries, the thermal bath try to thermalize the system and to put xt equal to p. Okay, if you forget this stochastic term.
Okay, for p term, you write Gibbs formula for p, yes, or something like that. So p is probability, equilibrium probability that you measure spin 1 or something like that. Yes.
It is given by the probes, in fact.
Gibbs formula for p.
Yes, yes. Okay. So xt tries to go to p. If you forget the second term is due to the measurements. If you didn't have measurements, you will have some just ordinary differential equation. And here, the second term will come from the measurement. As you see, there is a gamma that I mentioned before, which is the intensity of the measurement. So the first term is trying to put x, which is some number between 0 and 1, to p, which is a number, fixed number between 0 and 1. But on the other hand, you have the measurement. We try, in fact, to collapse the system, because if you send some probes which are prepared in some special state, they will try to make the collapsing of the system to 0 or 1. So you see x 1 minus x is 0 for x equals 0 or x equal to 1. In fact, if you didn't have this thermal state, you will have just dxt is equal to xt 1 minus xt dwt, and in the long time, you will have collapse to 0 or to 1 with some certain probability. So you can recover the collapse in this sense by just iterated interaction with the probes. So, but let us look for the moment just at this. Okay, if you are not interested in quantum mechanics, you are just look at this stochastic differential equation, and you see that you have two competing effects. You have the thermalization effect, so x try to go to p due to the drift term, but on the other hand, we have some excitation by the Brownian motion, and this excitation becomes very big because there is a square root of gamma, and gamma will go to infinity. And so there is a competition, but this excitation of the Brownian motion is becoming very, very weak when x is close to 0 or to 1, despite the fact that there is a gamma which is very large. So there is a competition between these two effects, and if you look at numerical simulation, it is what you observed. So here on the top, we have a typical representation of the trajectories that you get. So you see that at the end, a priori, these trajectories are continuous trajectory of time. But in large gamma, when you have strong measurement, it looks like a jump Markov process, but jump Markov process which is a bit special because you have some spikes which appear somewhere. If you smooth a bit the thing, smoothing, okay, you have several ways to smooth the thing, but you can, for example, you take a small time window around some time, and you average the value of xt around this time, then you can remove the spikes that we observed before, and you have a good jump Markov process, realization of a good Markov process. So the goal was, so one of the first goals is to understand how we can understand this convergence to this jump Markov process.
May I ask one more question about physical nature of this equation?
Mm-hmm.
Could you, some years ago, probably many years ago, it was a theory of continuous measurement developed by Slava Belavkin. Probably some colleagues could know him, and so-called Belavkin equation. Probably there is some connection between your equation you study here, and the Belavkin equation.
Yes, there is a strong connection. Exactly, there is a strong connection, and I was presenting just a way to understand these quantum trajectories, but you can present it in very different ways. So exactly, it is also called Belavkin equations, in fact.
Okay,
these quantum trajectories.
Thank you.
But in fact, just during the, I think it is at the beginning of the century, some people were interested again in in these Belafkin equations, but with a different aspect. But in fact, everything is related, and control theory is also related to that, and so on. So it is, my presentation is very elliptic. I don't present everything.
Thank you. I think it's very interesting.
So anyway, this is some examples where I want to show you what happens in a very simple example where you see the drift try to push the system to P. When it is close to P, then the noise is sufficiently strong to push the particle outside of P and going to 0 or to 1. When it goes to 0 or to 1, there is some noise, but the noise becomes very small. So the particle is not moving so much, and then it tries to go to P. And at the end, when you perform numerical simulation, you obtain some pictures like that. So this is a simple example in which you have just a qubit, so a system with dimension 2. Now I would like to say that we develop some theory in the case where you have a d-dimensional system. So it is more complicated, of course, and we were considering the case, which is a choice, where we have in fact 3 scales of measurements intensity. So it means that you have different measurement. You can measure the system. You have a system, and you measure the system, or you interact with the bath and so on, but with some certain intensity, which are regulated by some parameter gamma. Okay, and it is a choice.
Sorry for interruption, just a few questions. Okay, we are a bit familiar with open quantum systems, and I have problems with your slides. For me, as I was told in the basic physics course, the Krauss operators, this is partition of unity, and L is not Krauss operator, it's some infinitesimal part. So Krauss operators, they sum to 1. These operators are more or less arbitrary, so that's not quite clear for me, because as I was taught in physics, Krauss operators partition of unity. Operators for Belafkin types equations, as was mentioned, I used to know him quite well. They are arbitrary. Why you call them Krauss operators? This infinitesimal part. Okay, they are computed based on Krauss operators, as I understand. These operators L, they are arbitrary matrices, but Krauss operator is not arbitrary. This is partition of unity, and if you expand them, you will have like infinitesimal parts, all these kind of operators which describe interaction with open system. Okay, do you understand me or not?
Yes, probably you are right. First, I am not physicist. In fact, and with my collaborators, I know that they were arguing about, should we call them cross operators? So maybe it is not the correct name.
Classical books, basic textbooks on physics, Krauss operators is partition of unity. We can expand them and take some infinitesimal parts of these operators. Then you will have arbitrary operators L, which appeared for open system equations. Okay, check it with your colleagues who are physicists, please.
Yes, no, I think you are right, and in fact, I don't know how to reply to your question. Maybe the cross operators is not the correct name. We should call them in a different way. It is just some of my collaborators say we can call them cross operators, mentioning some information theory, but it was not very convincing. So for me, they are just matrices.
Yeah.
And
L in this equation are arbitrary, absolutely arbitrary matrices, but across
Yes.
operate conditions. Okay.
Yes. Okay. Okay. But what will be the name that I should give to this Lindblad operator? So I have some Lindblad operator. It is written in this form with some LK. So what is the name to give to this LK?
Okay.
I don't know. It is so we call them cross operators, but okay, then probably is not the correct name. I agree. Anyway, in the more general case, so I presented just some example of a qubit, but in the more general case, you have a system which is living in some d-dimensional space. So rho t, which appear here, is now a matrix, which is a matrix of size d, a square matrix of size d, which is symmetric, which is Hermitian positive, and with trace 1, and which represents the state of the system. And in these quantum trajectories that I developed before, these stochastic matrices are evolving according to some differential equation. So before, the stochastic differential equation was very simple, as you have seen, because mainly it was just a diagonal which was important. The off-diagonal terms were going to 0 as the measurement was going to infinity. Here it is more complicated. And we were interested in the case where, in fact, you have three levels of interactions. So there is, so I recall you that gamma represents some measure of the some intensity of the measurement. So here it means L2 is the strong operator. L1 is some intermediate operator of measurement, and L0 is some measurement which is or it can be measurement or it can be Hamiltonian, which is very small. And due to the theory before, we get some stochastic differential equation, which is a finite dimensional stochastic differential equation, but with a very special structure. Very special structure because first, the drift that you see here is given by what is called a Lindblad operator, which is a linear operator acting on matrices. So it is called sometimes a super operator. So rho t, I recall you, is some element of the matrices of dimension d. So you can see like a d square stochastic differential, d square dimensional stochastic differential equation. And so the structure of this drift is not arbitrary, it has a special structure. So here I write the typical structure of a Lindblad operator. So here, if you are a bit familiar, it is the part coming from the Hamiltonian structure of the quantum system that you want to describe. So with some Hamiltonian H. And so it is a commutator between H and X. So X will be rho as a density matrix. And here there are a part which is coming from various terms, which can be measurements, which can be interaction with some thermal bath. Everything can be encapsulated in this kind of operators.
Okay. And I imagine the last term is anti-commutator or something. Last term.
Yes, exactly. And so I will not discuss too much, but I want to say that you have a quantum. So you have stochastic differential equations. The drift term is quite very nice because in fact it is linear. As you say, it is just L gamma is a linear operator. What is non-linear is the term which appears in front of the diffusion. In the diffusion, you have three different terms, so gamma 1/2 and gamma. And these, of course, these diffusion coefficients are related also to the drift. So then they are not arbitrary. So they are.
Yeah. Okay. In your one-dimensional example, it's intuitive, what should be proved, but it's intuitively clear that the particle will jump between 0 and 1, which are zeros of diffusion. Here we have three different coefficients and they have different zeros. So how to guess, not prove, but to guess, what are the points between which points the particle will jump in the limit? Should I take the highest zeros of sigma 2 or what? How to guess between which points you have jumping process?
Yes, I will come. I will come to this point after. I will come exactly to this point, which is an important point. Yes, why 0 and 1, and in this general context. So I will come to this point a bit in a few minutes. So, but okay, I don't want to that the people are confused with this because it is. If the people don't know this quantum mechanics and these Lindblad operators, it's a bit complicated to see. But you have some stochastic differential equation with a linear drift and with a quadratic fluctuations. So now. Why it doesn't work? Sorry. Yet. What is that? Sorry. Mm-hmm. You see my screen?
Yes.
Yes. Okay. So in this talk, I would like to present mainly three results. So the first result is a convergence in some special topology that I will describe a bit later in the strong measurement limit of the quantum trajectory, general quantum trajectory, to a Markov process, continuous time jump Markov process, and identifying exactly what are the points between which I'm jumping. So to reply to the question. And in the second point, I will describe a bit more precisely what are these spikes. But these will be restricted to the one-dimensional case. And in the, if I have time, I will, in the third part of the talk, I will discuss some connection with some filtering problem. More exactly, the Shiryaev-Vonham filter. So first main result, which is some homogenization theorem, in fact, when gamma goes to infinity, when the measurement becomes very large, and there is a weak convergence in distance to a pure jump Markov process. So I recall the context. So you have some quantum trajectories, which is written like that. So I recall you that L gamma is a linear operator composed of three terms. And these three terms, okay, they have not the same importance because the gamma square L2 is very strong with respect to the other one. So there are three intermediate operators, but they are linear. The sigma are quadratic operators. And here you have some different Brownian motions, which are d-dimensional Brownian motion. So since, in fact, there is a very special property of his stochastic quantum trajectories, is that phase L gamma is linear. So if you take the expectation, then you, of course, the martingale terms disappear, and it remains only the drift term. But the drift term is linear. So at the end, you get that in mean, the average of 40 gamma is just the semigroup generated by L gamma. So L gamma is a finite dimensional operator multiplied by the initial condition. And the first step is to understand what is the behavior of his semigroup, exponential of TL gamma. So if you want to see it in a different way, you can say that, okay, if you write this TL gamma, so a gamma is written here, so you put gamma square as a common factor, you see that in fact I'm looking at the long time behavior in this time scale T gamma square of the generator generated by L2 with some small perturbation, 1 over gamma and 1 over gamma square. So L2 is the most important term, but it is, we'll see that L1 and L0 can have some influence. So if you look at his problem like that, and if you want to understand his the behavior of his semigroup, you can say that it is a standard finite dimensional homogenization problem. But it is not exactly that, because first, it is not so easy to identify what are the slow variables and what are the fast variables. You know, in this homogenization problem, usually you have some clear identification of the slow variables and the fast variables. I say slow variables will converge very slowly, and so the fast variable will average around the behavior of his fast variable. But here it is not a priori, when you see the stochastic differential equation, it is not easy to see what are the slow variables. And the slow variables, in fact, are the kernel of L2, because if you have some rho which is in the kernel of L2, it means that this guy will not contribute, it will not move, and so the other part will try to average around this slow variable. And the second point is that when you fix the slow variables, the dynamics is not ergodic. So you cannot resume it to a standard homogenization problem. So we established some general results, which is probably true in infinite dimensional, for infinite dimensional operators, but probably with some extra conditions, but we establish it for finite dimensional operators. So, and it is independent of the structure of Lindblad structure of the operators. So imagine that you have finite dimensional operator L gamma with these 3 scales, L0, L1, and L2. So for the moment, I don't assume nothing about the structure of L0, L1, and L2. They are just operators from finite dimensional vector space to some of the finite dimensional vector space. And I introduce P, which is a projector. The projector onto the kernel of L2 parallel to its image. So it is defined in this way by some ergodic average. Of course, in order that this limit is existing, you need some spectral properties of L2. For example, all the eigenvalues of L2 have to be negative. Otherwise, you have something which is diverging. But you need a bit more. You need a bit more. You have to be careful with the Jordan blocks of L2 and so on. So we assume that phase 1 is existing. We assume some bondedness, uniform bondedness of the semigroup generated by L gamma, and we assume some centering condition of L1, which is an intermediate one. And in this case,
Excuse me, could you possibly show the formulas for the limiting transition rate of your jump process? There should be some explicit expressions, I imagine, that imagine the limit of transition rates. It should be finite dimension, Markov chain with finite number of states, so it's defined by the matrices, as we all know, and probably you have formulas for transition rates.
yes. Probably it is in the slides, I think, but yes, we have at the end we have some explicit formulas. But a priori, if you start with some arbitrary operators, it is not so easy to, for example, to compute P exactly, to compute the eigenvectors and so on. In this case, it would be possible, but it is because of the spatial structure of the Lindblad operators.
Okay, but you have your dimension fixed, right? So if D equal, for example, 2, you should be able to express everything in Pauli matrices. You know, for D equal 2, it should be more or less explicit, I imagine, because you have Pauli matrices to express everything, but your D is fixed anyway.
Yes, for the moment I didn't say the hypothesis. Yes, it's true. For which, at the end, we were able to have some explicit expression, but it really depends on some special conditions. But if this generic theorem is true, even if we can compute nothing, because at the end, you see, you have some green function which appears here with L2 minus 1, which in general you cannot compute. I mean explicitly. What we say at least that we can prove the existence of the limit. The limit of the semigroup is given by this projector. So it is the projector multiplied by the semigroup generated by L infinity times the projector, and this L infinity is given by this expression in which you have L0, L1, and L2, but minus 1. L2 minus 1, in general, you cannot compute it explicitly. From even if I give you some matrix 4 by 4, it's not, you cannot do it. A priori, it's not possible to do it. But we will see that under some conditions, which are motivated by physics, we can compute explicitly this operator L infinity. And this L infinity will be the generator of a pure jump Markov process. I don't know if I replied to your question or...
Yes, thank you.
So exactly, so to reply to your question, so if this is a previous theorem, is a general theorem, but it is valid for arbitrary operators, and now we want to apply it in the case of Lindblad operators, which appears in the quantum trajectories. And to apply this theorem to Lindblad operators, in particular, we need some spectral properties to check, and we have to make two assumptions. So maybe I don't want to detail so much, and first because I don't know so much about it. So we have two assumptions. It is one is a non-demolition assumption, which is that, okay, it is written here, okay, Krauss operators is maybe not the correct name, but these operators, which appears in the definition of the Lindblad operators, the Hamiltonian operator, which appears in the main Lindblad operator as well as the L1, which appears in the intermediate operators, are commutating. So it means that they are all co-diagonalizable in a common orthonormal basis, EI, which are called the pointer basis. And then the kernel L2 is then the vector space of matrices diagonal in the pointer basis. So in part, it replies to the question before that it is a way to identify what are these points on which we live the system, the limiting system. This is this point, this pointer basis.
You see, sorry for this. Okay, these operators are arbitrary. Okay, physically. And so
is LK. You mean the LK?
Are arbitrary, but and
Yes.
you put some very strong conditions these operators. Okay, which is a bit problematic. And do you have some physical examples where these conditions are satisfied? So that you can show, because here they are arbitrary, and to put some conditions that they all maybe in one basis they diagonalize. It's a very strong assumption, very strong. On arbitrary, you see.
Yes, I agree with you. It is very
more or less explicit conditions which are physically interesting, because in physics they are arbitrary matrices, okay? And you, of course, you cannot simultaneously diagonalize them. There's no point to say it generically. Okay, but maybe you have some interesting physical examples when this is the case. That is interesting.
I know that, okay, I am not physicist, I am mathematician, so I just was listening what the physicists were saying, but some physicists like Bauer and Denis Bernard, they were saying that there are examples in which you have these conditions. Now to explain why exactly, I think it's mathematically it's not so difficult to create these operators which are commutating.
Okay, well,
now what's your
zero on physical problems, because physically this arbitrary matters, and so you study some measure zero in the set of all physical systems, and you should be able to explain why this specific surface is physically interesting. You see, because generically there's no point to say that in generic physical system they are simultaneously diagonalized. It doesn't make sense. You should have very concrete examples that explain why this manifold of dimension zero has some importance in physics. That's how I see the problem.
Yeah, I understand your complaint, and yes, you're right. In fact, I should have some example to argue why physics interesting to consider these cases. I don't have, but I know some people who say that it makes sense. Some physicists saying that it makes sense to consider these conditions. But it's true that I don't have, so I cannot reply to your question now. It's true, but you are right to ask this question, just because I was a bit lazy to really go to the details of the motivation to impose this non-demolition assumption in concrete examples. So I don't know how to reply to a question. I don't have the answer. I'm sorry. And okay, this is one of the conditions, and so all the operators which are that I mentioned before, the LK2, H2, LK1 are all co-diagonalizable in a common orthonormal basis E1, EI, which are called the pointer basis. And there is a second condition which is a bit more exotic, which is called the decoherence assumption, which is, okay, probably you don't remember what is this eta 2k. This eta 2k appeared here. There are numbers between 0 and 1, which represent, in some sense, the fact that you are measuring more or less strongly the system. So in particular, they can be 0, for example. So it means that they are not appearing. You are not reading the result of the measurement. And his assumption is that if eta 2k is positive, then you need this condition here, that I understand mathematically, that physically I don't well understand. But it was necessary to have some decoration of the off-diagonal terms. So it is called the decoherence assumption. But I am not very familiar with that, in fact. So what I wanted to point out about this problem is that, so then we can use this homogenization theorem, and so under the previous assumption we can apply this homogenization theorem to our operator L gamma, which has a special form, which is a Lambdadian, and we can show that in mean. So it is in mean, here you have the density matrix, it converges to the expectation of xt star. So xt star is just the conjugate of xt, transpose conjugate of xt. So it is a matrix. And xt is a pure jump Markov process with state space, the pointer basis ei, which are in fact the eigen which are the pointer basis ei are the ones that I mentioned here. The Hamiltonian H2, the L1, they are all diagonalizable in a common orthogonal basis, ei. And this is, for example, in the case of in previous case, two-dimensional case, it is just 0 and 1. Okay, so this is just a convergence in mean, and you say, okay, convergence in mean is not so good because you would prefer to have some convergence in the sense of the trajectory, in the sense of the path. And here it is just convergence in terms of the mean. So here there is a problem, if you think, because rho t is a solution of a stochastic differential equation. So it means it has continuous trajectories of time. This process here is a pure jump Markov process. So it doesn't have continuous time trajectories. It has some jumps. And so it means that you cannot use the usual standard, the usual square code topology. Square code topology, if you start with some trajectories which are continuous, and if you are taking some weak convergence, then the limit will have some continuous trajectories. So you have to use some different topology. So the topology that we were using, that we called Meyer-Zhang topology, but in fact it is probably a bad name. It is the topology of the convergence in distance. So which is defined here. So it means mainly that we are just looking the L0 convergence between two paths. And fortunately,
so you relax the topology with time, which is natural. Yes, correct. So the longer the time, the weaker conditions on the topology. You relax somehow your topology with time. It's more strong at the beginning for small t, and is relaxed gradually with the increase of t. It is correct.
Yes, it is correct. We relax the topology. The scalar topology is too strong. It is we cannot get the convergence in this topology. So we have some topology which is weaker. But it is okay. Mathematically, it is a bit problematic because this space L0, the space of measurable function of time with values in the space of matrices, is not a Polish space. So you cannot use the Prokhorov theorem. But fortunately, this Meyer and Zhang provides some alternative way to prove some tightness. And thanks to this tightness criterion of Meyer and Zhang, we can show that in fact rho t as a path is tight in this space L0. And okay, then there is some work by using the Markov because here we have just a convergence in mean. So say convergence in mean, how to get the convergence for the multidimensional how say to the multidimensional I lost it. It's okay.
Setting.
Yes, exactly. So thank you. And so there is some work to perform, so that I will not describe here. But at the end, we get this theorem. This theorem, which is that we have that at the process. So it is in this spatial topology. So if you smooth means that you take some function, test function f, depending on time and on the state space. Okay, this is exponential minus t to avoid the problem at infinity in time. Then it converges to this jump Markov process. And this is quite general under the assumptions that I did before. And we provide in some way something that which was predicted by the physicists, that we have some jumps in quantum trajectories in the strong measurement. You start with some quantum trajectories which is continuous trajectory of the density matrix, but when the measurement is sufficiently strong, then you get some jump Markov process at the end, which describe the effective nature, the effective motion of the density matrix of the quantum system. So this result is not totally new in the sense that it was predicted also by non-rigorous method by Denis Bernard, Antoine Tilloy, and Michel Bauer. They got also this result, but it was not rigorous. Here, it is a completely rigorous result. And the method is very different, in fact. So this is the main theorem that I wanted to prove, the convergence to the Markov process, jump Markov process. And now in the second step, I would like to discuss the case of spikes, which is much more exotic in some sense. And so for this spikes process, we are only able to do it for mainly systems which are one-dimensional models. So I present one. We can also do it for Rabi oscillations, but mainly they are one-dimensional systems. So I'm starting again with this stochastic differential equation. As I told you, gamma will become very large. So there is a competition between these two terms. This term try to push the xt to p, and there is this term which is exciting the system, but the excitation becomes very small when x is close to 0 or to 1. Anyway, this stochastic differential equation is living between the interval 0, 1. And if you rephrase what I said before, the previous theorem, in this case, then what we proved before is that we have the limit of xt gamma to xt in this Meyer-Zhang topology, if you wish, where xt is a jump process between 0 and 1. So this 0 and this 1 are what I called before the pointer states. More exactly, what we can prove is that you have some decoherence, so the off-diagonal terms goes to 0, and only the diagonal terms survive. And you have xt on 1 minus xt, and this xt is the jump Markov process that you see here, jumping between 0 and 1, with the rates which are completely explicit. Also in the previous case, they were completely explicit. In the multidimensional case, they are also completely explicit. Lambda p and lambda 1 minus p. But now, this picture here on the bottom is obtained by smoothing the thing. It means that when you take a time t here, you average in a very small time window around this time t in order to get something nice. If you don't average, in fact, you always see these spikes everywhere. And so the question is, understand these spikes. What is the statistic of these spikes? So the theorem that we got, so it is restricted to one-dimensional, but it is the following. So let me remark that, in fact, if you look at this thing which is here, it is not the graph of a function, because you have some spikes. It means that on each point on the horizontal axis, you have several values. So you cannot consider it as a function. So the idea that we had was to consider that it is a graph in R2. And so what is, if you have a graph in R2, how to compare two graphs, a graph of function and a graph in R2? So one idea is to use a Hausdorff distance between graphs. So I consider A and B, which are two-dimensional object. And so it is a usual definition. You see, you take the smallest epsilon such that A is included in B plus epsilon B. B is a unit ball in R2, and B is included in A plus epsilon B. So it is a usual distance to measure the distance between two-dimensional objects. And what we say is that, in fact, with xt gamma, okay, here it is marginal. In fact, it is marginal than just the equation that I presented before. We just need that B, the drift term, and sigma are satisfying the condition, the following condition. So B1 is negative, so it means that when your particle goes to 1, the drift tries to push you to the interior of the interval 0, 1, and B0 is positive, so it means that when you try to go to 0, the drift tries to push you in the interior of the interval 0, 1. And at 0 and 1, the volatility which is here becomes very small in some sense. Of course, there is square root of gamma, which is very large. But since it is 0 here, it becomes quite small when you approach the boundaries. So at the end, your trajectories is always between 0 and 1, and it will basically it will have the same behavior that what we have seen here. It will be close to 0 for a long time, with some time trying to escape. One day succeeded to escape until 1, then staying close to 1, then going to 0, trying to escape, going to one. So here it is a special case, but in more general case of SDEs, you have this behavior. And we prove that with this Hausdorff convergence of graphs, here most surely we have that xt gamma converges to xt. So we describe this process X by words, not by equations. So first, you draw in red, you draw the gem Markov process that I described before. So it is a gem Markov process that we obtained before. So here I say, you know, the rates are lambda p. So lambda p is just the drift evaluated at 0, and lambda 1 minus p, just the drift evaluated at 1. So in the marginal case, here the rate is b0 and b1. So the rate to pass from 0 to 1 is b0, and the rate to pass from 1 to 0 is b1, where b is the drift term here. And then you have to decorate this Markov gem Markov process by some spikes. How you obtain these spikes? What you do is that just you put some point person process with okay, when you are here, you put some point in this point person process, so two-dimensional time and space, with intensity which is in time, it is just b0, absolute value of b0 dt, and here dm divided by m square. So it means that in fact you have a lot of small spikes that I didn't draw here, because it is dm divided by m square, which is not integrable. And when you are here, you change the intensity, which becomes b1, absolute value of b1 dt in time, times dm divided by m square. So for the people familiar with Brownian motion, the dm divided by m square should recall something related to the excursion theory of Brownian motion. And in fact, it is related. Okay, I don't have so much time, but let me continue a bit. Okay, so this is a theorem that we establish, and this permits to understand the statistics of the spikes. We have a complete picture of these, not only of the quantum jumps, but also of the spikes. So I will go briefly to the proof. The proof is not very complicated, in fact. The idea is to introduce some harmonic function, h gamma, for the diffusion process. So it means that if I introduce this harmonic function, so it means a function, so if I write the generator and so on, an harmonic function, so what I get is that h gamma of xt gamma is a continuous time martingale with a quadratic variation which is given by this expression. And here h gamma is quite explicit. It is explicit in terms of b and sigma. It is just second order differential equation. So it means that h gamma of xt gamma is a martingale. So by the Debye-Schwarz theorem, it means that it can be expressed in law as a Brownian motion change in time. So xt gamma is this harmonic function, the inverse of his harmonic function, evaluated to this Brownian motion. And thanks to that, in fact, we can also compute the derivative of this inverse of this change of time. It is quite explicit with some explicit function phi gamma here, and this phi gamma, which is completely explicit function depending on gamma. When gamma goes to infinity, we observe that it converges to this very simple expression, 1 divided by 2b0 delta 0, direct mass in 0, plus 1 of 2b1 delta 1, direct mass in 1. So it means that we have some almost sure convergence in terms of the local time of the Brownian motion, of this change of time. Then we introduce the inverse, the pseudo-inverse of this mixture of local times, and we can write this ft xt gamma, we can write it like in the following way. So the t we change is the t is changed thanks to this change of time t gamma. So it will converge to sigma s minus 1. So here it is minus 1 because, of course, this function is not invertible because it has some flat part. But so it is a pseudo-inverse as defined here. And since we know that it converges to this mixture of local time, we get that it converges to this guy where it is Brownian motion evaluated in sigma t, where sigma t is this inverse of the mixture of local time. It turns out that if we perform the computation, this Brownian motion evaluated into the inverse of this local time is in fact just a jump Markov process between 0 and 1 with rate, which are written like that. It is very complicated way to write a pure Markov jump process between 0 and 1 with the local times of the Brownian motion, but it is something that you can check easily. And so this is some alternative proof to prove that you converge to the gem Markov process. And for the spikes description, it is a bit more complicated. We have to use the Ito's theory of excursion. But that I don't have time to explain, I think. So at the end, so the main message is that we are able to prove this second theorem. We are not only able to prove the convergence to the gem Markov process, but we are also able to describe the statistics of the spikes in a very precise way. And it remains some difficult problem to extend this theorem in the case where you don't have a qubit, for example, because here it is the proof rely on n-dimensional properties. We use harmonic function and so on. And for multidimensional system, it will be very, it's much more difficult, and it's clear that we need to use different techniques. Okay, if I have only 5 minutes now, I would like just to mention something which is not related to quantum mechanics, but which was a bit surprising for us, but which is this problem of filtering. So it is called the Shiryaev-Vonham filtering. The Shiryaev-Vonham filters. And the question is very simple to understand. You imagine that you have a time jump Markov process X on 0 and 1. Okay, so jumps from this continuous time. So it is 0, then jumps 1, jumps 0, jumps 1, and so on. But you don't know it. You don't know the rate. And you try to estimate these rates, or you try to estimate the state of your Markov process, but what you have access to a signal which is a perturbation of the original Markov process xt, which is perturbed by some Brownian motion, but the perturbation is very small. So it is 1 divided by square root of gamma, and gamma is very large. So it means that you have a very small perturbation. So a priori we can say, oh, it's not a very big problem. I have just to measure, to estimate this system with a very small noise. But we wanted to understand, okay, it happens in some situations that you can not do it directly. there are situations in which, for example, if you want to estimate at time t, you receive the signal until time t, but for some reason you need a bit more time to evaluate. So it means that you have to observe the signal a bit later than t in order to deduce the value on t. So for technological problems. So if you are in a perfect world, what you do? You have to have some estimation of your process. What you do is that just you evaluate the probability of xt is equal to 1 given the trajectory of the signal that you observe until time t. And the Shiryaev-Vonham filter show that phase xt gamma here, which is the best estimator that you can expect in some L2 sense, is given by phase stochastic differential equation. Now, if sometime you need some delay in order to estimate, so it means that if you want to deduce the value of the process at time t minus delta, you need to observe the signal until the time t. So you observe a bit later. So delta will be small. And in this case, you have also some filtering equation, but filtering equation which are a bit more complicated, which are expressed here. And what is the danger here? What is the danger is that if you remember, so this equation is exactly the equations that we have seen before appearing in the quantum context. And you have seen in the quantum context, this equation had some spikes. So sometimes when you have a spike, which is sufficiently high, you can confuse with a jump. And you can think, or your filter can think that the spike, in fact, corresponds to a jump from 0 to 1, and can interpret the value of xt, of capital Xt, as 1 instead of 0. So these spikes have some impact. You have to be careful with these spikes. They can produce false information. And if you have a filter which is a bit more smooth filter, so you ask some delay in order to not take risks. So you could expect that by waiting a bit before to take a decision, then you will be able to give some correct decision. And what we proved, in fact it is in progress, it is not totally proved, is that if the delay is sufficiently large, then everything will be okay. So if this delay depends on gamma. Gamma 1 over square root of gamma was the intensity of the noise. So if this delay, which is given by here, is sufficiently large, then it is okay. You will recover your process. You will recover exactly the 0 and 1. But if you take a delay which is too small, then you can be in trouble because you could have some spikes that you didn't expect. So it has also some implication. This result that we discovered on the spikes processes has also some impact on in these filtering problems.
Sorry, but gamma looks negative in your formula.
No, gamma is very large.
No, log gamma is small.
No, gamma. No, gamma is large because you see it is 1 over square root of gamma.
Okay.
So it is a small noise. It is a small noise, but so gamma is large.
Mm-hmm.
So delta gamma becomes small. Okay, it's written this way. You see, if C gamma is constant, delta gamma is of order log gamma divided by gamma. So it is a small constant. So you don't have a big delay. You take a delay to take your decision, but this delay has not to be too small. If it is too small, then maybe you could make some errors of predictions. So I thank you very much. I think I finished to present everything that I wanted to present. Maybe it was a bit fast at the end. Maybe there are too much material, but okay.
Okay, excuse me. Could I just check what is the message to take home? You have three scales, three operators L0, L2, L1, L2, every scale, and three diffusion coefficients. I imagine that you should have some simple procedure to first to say what is the number of states of this limited Markov chain, and then some explicit expression for transition rates between these states. And I'm not quite sure that I have seen this. What I expect from your talk, you have okay. You maybe you take zeros of the highest term for the diffusion, but it's not completely clear for me from your talk. So you should have simple algorithm that give you the number of states of the limited Markov chain first, and then some simple procedure that give you the limited transition rates. Okay. And if you can show these formulas, I'm not quite sure that I have seen them.
Yes, no, you are right. And in fact, the number of pointer states that I call EI here, they are on size D. They are D, which are the size of the density matrix.
Okay, so you statement is all the D states. Okay, and can you please show that D by D transition matrix, limited transition matrix?
Yes,
this.
and but we have also the explicit expression of the transition rates.
Yes, obviously.
Yes, we have then, I don't know if I use paper here. Oh, it is the best version. Yes, here you see there is in this formula. I don't know if you see it.
I see some eigenvalues, but this is not exactly what I'm asking. The D by D matrix, which with some signals to zero and positive off diagonal terms. What I want to see is what we teach. The basic course of Markov chain. D by D matrix, which has negative elements along main diagonal, positive elements outside the main diagonal with some zero against every row. That's what I expect to see.
The off diagonal terms, you mean?
Of course. Okay. Off diagonal terms of this matrix. Okay. But this I read some eigenvalues, which is not completely what I'm asking for.
Yes, but the eigenvalues are related to the rates.
They're related, but I imagine that at the end of the story, as I imagine this story, that you should demonstrate this D by D matrix, at least of course no diagonal elements of this matrix. What I would expect from your story.
Yeah, in fact, the D by D matrix, you see here, it is EI, EJ star.
I understood that. You say that there is these states. I understood it. Okay.
Okay.
But I also want to see the transition matrix, which is would be natural.
Isn't that? No, but we have the. Oh, I don't know if it is written somewhere, but clearly. Because you know, at the end, the limit is given by x star, and x, it is just a jump process on 1, 2, 2, 3 until D.
Understood. But also we should say, okay, this is the limit. You have this discrete continuous time macro chain with these states with a transition matrix given by some explicit formula. What I would expect.
Yeah, but I have some explicit expression here for the X process, the process X, the jump Markov process X, the jump rates are given by this expression.
Okay. So you are saying that 2,8 gives this out of diagonal elements. That's what you are saying or not?
Yes.
Okay. So how it depends? 0 here, 1 here, 2 here. Okay. All three levels are involved. That I understand.
The only terms which are not appearing is L1. You see, L1 is not here.
L1, H1 is here, L1 is not here. Okay. Okay.
Yes.
Thank you for your comments. Okay. I understood the answer. Okay. Thank you.
More questions? Comments? Okay, if it's not the case, let's thank the speaker.
Thanks.
Thank you for everybody.
Thanks.
Thank you very much for very interesting talk. Valentin Dmitриевич, could you hear me? Could you please stay here and I have a short talk to you?
Okay.
After this,
probably, yeah, after this meeting.
Of course, we can talk.
Okay.
Thank you. What about the next talk, Alexander Viktorovich?
I know that Arab accepted the invitation, he will give a talk. That's Jean-François, is it correct or not?
Yes, I told you. I said that I shot Axiom can give a talk next week.
Is it for sure? Because Alexander Viktorovich proposed to wait until tomorrow, but I don't know. Maybe we'll accept this.
You what to say?
Just a minute.
Okay, go ahead.
As I understood, the speaker has already given his agreed already to make talk next week. So okay. So if it's the case, so we indeed have this talk next week. What is the name of the speaker? Sorry, I forgot. Okay, great.
We will write exactly the names, the title, the short resume also. It will be ready maybe in 2-3 days. Okay.
I'm sorry, but this seminar is every week or?
Yes.
Normally, yes, one times in a week. If you like, we can include you in the
The list.
okay, in the list.
Yeah,
Yes.
yes, it will be good.
Yes, yes.
Okay.
Okay.
Okay, so thank you and good evening.
So we
thank you.
finish. Just
Yes, Maria, could we speak 5 minutes after this seminar? Don't switch out this Zoom.
Okay, it will be on. It will be on. I will just stop recording.
Yes.
Okay, done.